Hello, y'all. We are in section 8.6 now. This is the convolution and the convolution theorem. So this starts off with some blurb about what's happening. We know for the Laplace transforms, we satisfy the sum and the scalar multiple constant thing, where the Laplace transform of the sum is a sum of the Laplace transforms, and the Laplace transform of the constant times a function is a constant times the Laplace transform of the function. Inverse Laplace works the same way. But what about if we have a product? So when we're adding, subtracting, okay, we can do that easily, but if we have a product, can that work out the same way? The answer is no. However, in taking derivatives, we have the product rule, and taking the antiderivative, we have the integration by parts, kind of like a backwards product rule. But when we're doing Laplace transformations, we have what's called the convolution. And so what is the convolution? So here they go through some sort of motivation, and it's usually going from the Laplace world back to the real world that would be an issue. So that's the inverse Laplace business. And in the Laplace world, we could have two functions or two functions that could easily transfer back as functions by themselves. But if you have a product of them, it'll be a little bit trickier. So how does that transfer back? Well, it's going to transfer back, it turns out, as a convolution. So here's their motivation. You have a second order differential equation with some forcing function and some simple initial conditions that are all equal to 0. And so this transforms to y times this polynomial as, this quadratic, as squared plus bs plus c. And then on the other side it's just fs. And so if you solve for y is going to be fs divided by this quotient, or divided by this polynomial, or you can write it as g written as a fraction. So now if we can transform this easily back, then that would be great. That would be wonderful. And so here's an actual example, simple first order linear. And we know that if we do the homogeneous portion, we're going to get a solution, and then we just need to multiply that by f of t, and then we go through this business, and then we have this expression. So this expression looks like it might be a good candidate for the Laplace or the convolution. And in fact, they go through a little bit more work of some of the things here, and they get to this function. So the inverse Laplace of f times g is going to be this thing. So this thing clearly is not just a regular product of little f of t times little g of t. It is this more complicated integral. And that will lead us to the definition of the convolution. All right, so that's a little preview. And the convolution itself is defined to be that integral that we just saw. Now, they use tau here. I know it's confusing because there's t's and taus, and they're essentially the same. And so you have to be careful how you write it. Some books just write x here just to get it over with and say, hey, that's just a dummy variable that you're dealing with. But for some reason, the convolutions, they use tau. We're not going to prove this formally, but the convolution is commutative. And so if we switch the order of f and g, we're going to get the same result. And so that gives us freedom to use whatever might be more convenient for f here. And then the g is the one that has that shift, t minus tau. All right. Here are a couple examples. Let's find the convolution for each of these. So how are we going to find the convolution? Literally just write that function. And here I'm going to go ahead and quickly take advantage of that business about the convolution being commutative. And I'm going to quickly I'm going to call this f of t, and this is g of t. Because, again, it doesn't matter. This is squared, so I don't want to mess with, t minus tau quantity squared. So I'll say 5t squared convolution with 8t is going to be the integral from 0 to t of 5 tau squared times 8, and then the t now has a shift t minus tau d tau. All right, let's go ahead and integrate that from 0 to t. I'm going to try to do this carefully. This is going to be, let's go ahead and multiply the 5 times 8. That's 40 tau squared, and then t minus tau. So I'll go distribute that in the next step. 0 to t, 40 tau squared times t minus 40 tau times tau squared is tau cubed d tau. Now remember, we're integrating with respect to tau. So the integral, we're going to treat t as a constant. So this is going to be 40 tau cubed over 3. I want to write 40 over 3 tau cubed, and then t is just hanging around as a constant. And this is minus 40 over 4 tau, that's a tau, not a t, tau to the 4th. So this is 40 times tau to the 4th over 4. And then we're going to evaluate the tau is our variable from 0 to t. So we know when we put 0 in here, everything's going to disappear. So if we put t in here, this is going to be 40 over 3 t to the 4th, and minus 40 over 4. I guess that's just 10. So let's might as well just write 10 t to the 4th. And they have the same, they're like terms, and so let's combine them. This is 30. 40 minus 30 is 10. Is that right? 10 over 3 t to the 4th. Okay. Yes, I think that's correct. All right, so that is the result for this particular convolution. Here's another one. Let's try this one. This one, I guess they're the same. It doesn't matter which goes where, so I'll call this F, and then this one G. And so the convolution here will be equal to the integral from 0 to t of the first function, e to the negative 3t, times the second function with a shift. Oops, this is not t, but this is tau, so this is tau. Times e to the 5 times t minus tau d tau. And so we're going to integrate this from 0 to t. I think I can combine this. I combine them, I add them, so this is just one exponential function. I have a 5t, and then a minus 5 tau, and then I'm going to combine it with a minus 3 tau. So I think that's a minus 8 tau. And I believe with respect to tau, this is your u substitution up here, where t is a constant. So this will give us a 1 over 8th, and then an e to the 5t minus 8 tau. I think this should be a negative because this has a negative also. And we're going to evaluate from 0 to t. We're going to evaluate tau from 0 to t. And then we have to be careful because if you put 0 in there, it's not going to fully disappear. So let's not neglect that. So I have a 1/8. And let's put t in there. So this is 5t minus 8t. That's e to the minus 3t. And then there's a minus 8 that's already factored out, so I'll just put a negative. And let's put 0 in for tau. This is 0, and this is e to the 5t. And I believe you cannot combine that into one. So I believe that is our result. Okay, cool. So now let's do the convolution theorem. The convolution theorem tells us, I think we should kind of highlight this, this is important, tells us how to go from the Laplace world to the real world, or the real world to the Laplace world. If we are taking the convolution in the real world, it is just the product in the Laplace world. That's what that theorem is saying. Okay, so it says verify this theorem, and they want us to figure out what the Laplace, I guess we should assume that they're looking for the Laplace transform here. So let me make a quick change. Script L, the Laplace transform of this convolution, according to the theorem, should equal to the Laplace transform. Yeah, am I gonna keep writing that? Sorry, I'm just doing some quick copying and pasting. So hopefully this will be true. I've got too many parentheses here. All right, that's better. So the idea is that they're supposed to be the same. These two sides are supposed to be equal to each other. The Laplace transforms of each of these things, the product is equal to the Laplace transform of this. All right, let's verify that. On the left-hand side, I'm not going to redo it because we did it over here already. This is the Laplace transform, or this is the convolution, 8t convolution with 5t squared. You get 10 over 3t to the fourth. So here we're actually looking for the Laplace transform of 10 over 3 times t to the fourth. So that one's easy, right? 10 over 3 is a constant. And then the Laplace transform of t to the fourth will match this as a 4 factorial, and then s, and then one more for the power, so that's to the 5th power. Can leave it like that. Sure. I mean, you could simplify. I think the 3's cancel and stuff like that. So we'll just leave it like that for now. And let's do this one. Let's take the Laplace transform of each of them. So the Laplace transform of 8t, so this is the Laplace transform of 8t, that turns out to be constant 8, and then the transform of t is 1 over s squared, I believe. And then now take the Laplace transform of 5t squared, so this is going to be 5 constant. And then the Laplace transform of t squared is, I think that's a 2 factorial divided by s to the third. All right. So let's simplify that. 5 times 8 is 40. Oh, let's go ahead and do this too also. So that's 80. 80 times 1 over s squared, s to the third, s to the fifth. Does that match? We didn't work this out. We got 10 over 3. We got 4 times 3 times 2 over s to the fifth. So this will be, let's see, get rid of the 3. 4 times 2 is 8 times 10 is 80 over s to the fifth, and it sure does match. So that works out. All right, we can do the same for this one. We'll go ahead and, well, let's see. Let's go ahead and do it. let's take the Laplace transform of this, Laplace transform of the convolution, which we got to be, let's write it just so it's positive, 1/8 e to the 5t positive minus 1/8 e to the negative 3t. So 1/8 e to the 5t minus 1/8 e to the negative 3t. And let me just take a peek to make sure that is correct. And so this, we'll break it up to two Laplace transforms, 1/8. And then this is going to be 1 over s minus 5 minus 1/8 1 over s plus 3. All right, leave it like that. Hopefully the other one isn't going to be too crazy. So once we verify this, let's see. Take the Laplace transform of each. So Laplace transform of e to the negative 3t, and then Laplace transform of e to the 5t. And then let's just multiply them. I think that's what we're supposed to do. And let's see. This will equal to 1 over s plus 3 times 1 over s minus 5. So it looks like we probably should do the breaking up business. So I'm going to call on Wolfram. Okay. And this has an 1/8 also. Perfect. Exactly what we had. So this is equal to 1/8, 1 over s minus 5. And then this is the minus 1/8, 1 over s plus 3. And it does match. So it worked out. All right. That's just to check your work. Now you can actually see the power of the convolution in these next couple of examples if all you're doing is the Laplace transform of this. Actually even more powerful when you go backwards. But let's just practice a couple of things here. Find the Laplace transform of the convolution of two things in the real world. And this will literally just be equal to the Laplace transform of the first function times the Laplace transform of the second function, sine 7t. And so this will be, if you remember, it's going to be, for cosine it's s squared plus 8 squared. And then this one is going to be 7, the constant, divided by s squared plus 7 squared. And so there's really not much you can do here. You can say 7s divided by s squared plus 64 times s squared plus 49. But that's fine. The same goes for here. So the Laplace transform of each of these things. So this is 1 over s minus 2 times 7 over s squared plus 7 squared, or 49. Okay. All right. So that's interesting. Let's actually apply the convolution problem, or convolution theorem, to a generic, kind of semi-generic situation here, where we are looking for the solution to this for some unknown f. So this f could be a simple function, it could be a piecewise function, or whatever. But let's just say if we were solving for this, how would we do it? All right. Let's see. And I think you do have homework problems similar to this. So let's take a look. All right, let's go ahead and do the transformation here. I think there's not much to do here. Let's just go to the Laplace transformation and get ourselves into the Laplace world. This is going to be s squared y minus s y of 0 minus y prime of 0. And then we have a 4y. That takes care of that. And then here, I don't know what f is, but let's just say it transforms to capital F in the Laplace world. All right, we got zeros for our initial conditions. So that's great. That simplifies things quite a bit. And then now we have s squared plus 4 times y equals capital F of s. Now, y, therefore, is equal to fs times 1 over s squared plus 4. Okay, so here's where we get to use the convolution theorem, regardless of what f is equal to. And we do this by a transformation back. So I think we're ready to transform back to the real world. Now we have y of t, and this is equal to the convolution of the transformation back from capital F. So that's just little f of t, that original function that we saw. And I don't know if you remember what this is, but I think the transformation for this requires just one little bit of step. I need, if I have a constant, I need that constant to match up to be the square root of 4, because this is going to be s squared plus k squared, and this k has to be on top. This goes for the sign. And so we need to multiply this by 1/2 to cancel with that 2, because that's what this is up here. Okay, so and this is the sine function, and so this will give us in our transformation back 1/2. Oops, this is a convolution back here, 1/2 of sine 2t. Now the 1/2 is constant, and you imagine this being in the convolution integral. You can move that constant all the way out, not a big deal. So you can have a 1/2 and then f of t convolution with sine 2t. All right, now you can be done here, or you can write it more as an integral, the convolution integral from 0 to t. The 1/2 is constant, so you can put that all the way out, and then you can have f of t minus tau times sine, not convolution, right? This is an actual times sine of 2t dt. Now, depending on how difficult your f function is, you may want to put the sine 2 times t minus tau, and then just have this as f of t, because it's commutative. You can switch the order of the convolution, but you can leave it like this, and this would be fine. So this is your solution for this problem. Okay. All right. Here's our next problem. If you want to pause the video a little bit, you can work this out, at least take a few steps before watching. So there is a 5-second pause, or as long as you want if you're going to pause it. All right. Here is our next problem. I think we're ready to go to Laplace world already. Not much to do in the real world here, so let's go to the Laplace world and remember our transformations for the derivatives. S squared y minus s y of 0 minus y prime of 0. That's for the second derivative. I have 6 times my first derivative, so that's s times y minus y of 0, and then I have a 9 times y, and then the transformation of little f is going to be capital F, which is an unknown function at this point. All right, let us gather some information here. Y of 0 is equal to 0. That's great. This is equal to -2. So negative will be a +2 on this side, but we're going to bring it over to the right side. So that will be a -2 again. Meanwhile, I have an s squared plus 6s plus 9 times y. And then let's see, this is f of s, and let's go ahead and bring this +2 to the other side, which becomes a -2. All right. So this is your formula. And then let us see what we can do here. Let's divide out. So then y is equal to, this is going to be fs, and I will put, is this thing a perfect square? It looks like it. S squared plus 6s plus 9. I think that's s plus 3 quantity squared. All right, s plus 3 quantity squared it is. 1 over s plus 3 quantity squared minus 2 over s plus 3 quantity squared. So since we don't know what f of s is here, this will probably be convolution, while this one is something that we can figure out. I hope we can figure that out. And I think we need to patch some formulas together for us to figure this thing out. And let's start off with 1 over s squared. That transforms into, I guess I should put the t, the real world usually is on the left side. So you have your g of t, and then your g, capital G of s. This goes back to t, I believe. And now there is this thing over here which looks like it's a shift. And remember what the shift was? This is a shift in the shift that's happening in the s world means that there is an exponential happening in the t world. So it's t, and then there's some exponential opposite sign, e to the 3t, and that will change your s into the s plus 3 in here. Okay, so this is they call it the first shifting theorem. In the previous section, when we're doing the unit step function, there is a shift that happens in the real world, and then you have an exponential function in the s world. Here, there's a shift that happens in the Laplace world, and then there's an exponential function in the real world. So there's like a backwards relationship with the shifting. So that is the shift function, which means these two functions have this shift thing going on. What does that mean? That means that when we transform back, which I think we're ready to do, Laplace inverse, back to the real world, our y becomes a little y of t instead of a capital Y of s. And maybe we'll do this one first. And we'll start off with a negative. There's a 2 here. And then after you take the 2 out, it's just 1 over s plus 3 quantity squared. So that's just the t e to the negative 3t. All right. Now, how does that convolution work here? So this is the convolution. This is going to be f of t convolution with this expression, which transforms back to t e to the negative 3t. All right, cool. So you could be done here, but if you want to express this as an integral, we can. So this is a negative 2t e to the negative 3t, and in here you have the convolution, and the convolution integral goes from 0 to t of f of t minus tau times, ooh, looking a little messy there, t minus tau times, not convolution, not star, but times t e to the negative 3t. Oops, that should be a tau. Tau e to the negative 3 tau d tau. All right, I hope that's what I did in the previous one. Oops, sorry. This should be tau. I just had a feeling that was wrong. Tau d tau. Okay, this should be tau d tau. And I believe that's it. So unless we know this function, this is about as far as we can go. Hopefully this function is a nice function that we can actually integrate this. If not, then, you know, we'll just Wolfram it. Okay, I hope that's good. There's a couple more convolution integrals and the Volterra integral equation. So let's do a couple more quick problems here. Say that the integral, it looks like this convolution integral that we've been seeing is called the convolution integral, and the theorem provides a convenient way to evaluate these integrals. So here is your example. So if you happen to be working with an integral that looks like this, you say, oh, how are we going to do that? What we can do is we can bring it to the Laplace world, because the convolution in the Laplace world is just the multiplication of two Laplace world functions, and then we'll just bring it back to the real world if it's easy enough. So to solve for this, kind of like what we've been doing all along, is to go to the Laplace world, and let's call this H, capital H of S. And this, by the way, we can identify this back in the real world as convolution of t to the 7th convolution with t to the 8th, right? So that's all that is. So in the Laplace world, this would be equal to the Laplace transform of t to the 7th times the Laplace transform of t to the 8th. All right, what does that equal to? That equals to, let's see, I think it's 7 factorial divided by s to the 8th power times 8 factorial times s to the 9th power. Well, I don't know what else we can do here. This is 7 factorial times 8 factorial times 1 over s to the 17th. Okay, so that's what we're saying. We are saying that h of s is equal to 7 factorial times 8 factorial times 1 over s to the 17th power. All right, so let's bring that back to get h. I mean, this is something that we can do, right? I hope. It looks like it's missing something. If I have 17 as a power down here, if you remember the formula, what is the formula? Recall that t to the n, the Laplace transform of t to the n is equal to n factorial divided by t to the n plus 1. So imagine n being 16, and then this will just come back to be t to the 16th. All right, but before we can send it back there, we need to have a 16 factorial in the numerator, which means we're also going to need to divide by 16 factorial in the denominator. So what does that give us? That gives us back now into the real world h of t in our Laplace transform is equal to a constant, 7 factorial times 8 factorial divided by 16 factorial, and then transform this back into t to the 16th power. And then that's it. So this is your solution for this particular problem. So if you have an integral that looks like a convolution, you have an opportunity to take it to the Laplace world, solve for it, and then bring it back up to the real world, provided that you have a simple function in the Laplace world that you can transform back easily into the real world. All right, one more topic in this section, and you know how we've been dealing with differential equations. A differential equation is an equation that has a derivative of a function that you're trying to solve. Well, we can also have an integral equation where you have an equation and you have a function y that you're trying to solve that's inside of the integral. So not just inside of the integral, but it's also convoluted with another function inside of the integral. So this is clearly another convolution problem where we can solve for this. The idea is to take this to the Laplace world, and so this is just going to be capital Y, this is going to be capital F, whatever that is. And since this is a convolution, this goes as capital K times capital Y in the Laplace world. So that capital A times capital Y in the Laplace world makes it now easy for us to solve for Y. We have a Y here and a Y here, and so you get the Y by itself, and you get Y is going to be the F function divided by 1 minus K. And then hopefully this is an easy enough function in the Laplace world that you can transform back. All right, here is our example of a Volterra integral equation, and let's solve for it. So let's bring this to the Laplace world. Laplace transform. Now we are in the Laplace world. We got y of s. T, I think that's 1 over s squared. And now here is your convolution of y of t, convolution with cosine of t, right? So I know there's a shift here, but the shift is inside of the integral, it's t minus tau. That just comes out to be t. So in the Laplace world, we have a plus. This will just be the Laplace transform of y, which is capital Y of s, times, not convolution, right? Just regular multiplication. The Laplace transform of cosine t. So that's s divided by s squared plus 1. All right, there you go. Now let's solve for y. Let's see, y. Let's bring this over to the other side. So that's going to be 1 minus s over s squared plus 1 is equal to 1 over s squared. This is just algebra, folks. S squared plus 1 minus s. Ooh. Didn't say it was easy algebra. Over s. Is that right? over s squared plus 1. And so we need the reciprocal of that to bring to the other side. So we got y is equal to 1 over s squared times the reciprocal of this, s squared plus 1 divided by, it looks like this is going to be an s squared minus s plus 1, which does not look like, unfortunately, does not look like an easy formula. It doesn't look like you can factor it. So I'm going to have to ask Wolfram how to get this together, or take it apart actually. So I have s squared plus 1, s squared times s squared minus s plus 1. All right. All right, upon consulting with Wolfram, I got this. So this is an irreducible quadratic. We will need to break that up, and we will need to, I think, be able to complete the square. So let us take it from here. That y will equal to 1 over s plus 1 over s squared plus 1 minus s over s squared minus s plus 1. And I think for us to work with this quotient, or work with this rational function here, I think we're going to need to complete the square and do a shift. Okay. So what does that mean? That means we need an s squared minus s, and we need a half of 1 is 1/2, square that is 1/4, and so this is a complete square. Plus 1, we need to subtract out the 1/4, so this would be s minus 1/2 squared plus 3/4. So that means in the numerator, when I deal with the cosine, that's the one with an s, I'm going to need a shift of an s minus 1. So in the numerator, I will need an s. So 1 minus s has to be somehow described with an s minus 1/2. What does that mean? That means I need to make this negative. Ooh, let me see. So this is going to be minus s minus 1/2 plus minus minus. So I'm actually adding a 1/2, which means I need to take out a 1/2. And then there's a plus 1 here. So this will be a plus 1/2 minus s minus 1/2. All right, I think that does it. Which means now I can break up this expression into a couple of things. So let's write y here again. I am out of room. 1 over s plus 1 over s squared. Those are easy. And now this is the tough one. I got a 1/2 over this thing, s minus 1/2 squared minus 3/2. So that 3/2 or 3/4, that 3/4 is going to play a little bit of a havoc with our our numerator, which means we need to kind of play around with something up there. But we'll do that in a minute. And then finally, this is a minus, and then s minus 1/2 divided by s minus 1/2 squared plus 3/4. This is a plus. Okay. All right. It looks messy, but what does that mean? These things are actually a shift. This is a shift with a cosine. This is a shift with a sine. Now there's something else missing with a sine here, and that is we need the square root of 3/4 up in the numerator. So the square root of 3/4 in the numerator, which will also counteract with the square root of 4/3. So we'll keep this square root of 3/4 in the numerator to get our sine function, and then we'll have the 1/2 and then this as a constant. Okay. Since I am out of room here, I will send this back to the Laplace transform to the real world. This, oops. I'm going to send it back here so that it's kind of in the same line. So the Laplace transform here, it's the same line of what's happening in the real world. Sorry for the confusion, but we are getting our answer up here, y of t. Now 1 over s transforms back to just 1. 1 over s squared transforms back to t. Now here's the other tricky part. I have a 1/2. So I'll do this down here because it turns out that 1/2 times the square root of 4 over 3 will cancel the square root of 4 into 2, and that just leaves us with a constant 1 over the square root of 3. And then this transforms back as a sine function. So this is a sine, and I'm leaving a space here because it's a shift in the s world. So this is going to be a sine of the square root of 3 over 4 t. And then the shift is a shift of a 1/2. So this is an e to the positive 1/2 t. All right, so there's a positive 1/2 t there. And this happens to be the easier one. After we did the hard work over here, this is just the negative. There's no other constants. And so that's just e to the 1/2 t cosine a square root of 3 over 4 t. All right, that is our result. And that is our solution to our Volterra integral equation. All right, and that's it for this section. Yay! So you'll definitely need to practice, and I think there's at least one of these in your homework. So get that done, follow these steps, and hopefully it'll work out. Good luck.